Good morning, everybody, and welcome to Sunrise Energy Metals update on Scandium markets and the Syerston Scandium project. I'm Craig Sainsbury, Investor Relations, and with me today we have Managing Director Sam Riggle and also the General Manager of Scandium Alloy Development, Tim Langan. Sam and Tim will give a presentation on the Scandium markets and the Syerston project. At the end, we will turn over to questions and answers. To lodge a question, please just use the Q&A facility at the bottom of your Zoom screen. Type your question in, and I'll ask that to Sam and Tim at the end of the webinar. Sam, with that, I'll hand across to you.
Thanks, Craig, and good morning or good afternoon to those who are joining today. Welcome to the webinar. Today's presentation will be slightly different to some of the earlier webinars the company has hosted in that it's timely, we think, now to start presenting to the market some information, not just about the Syerston Scandium project, but also the markets for Scandium that we have been working in and on for a number of years. As Craig said, I'm pleased to be joined today by Dr. Tim Langan, who is Sunrise's Global Manager of Scandium Alloy Development Programs. Tim has been with Sunrise for almost a decade now, and before we kick off, I might hand over to Tim so he can introduce himself to the webinar today. So Tim, to you.
Sure. Thanks, Sam. Yeah, my name is Tim Langan. I'm up here in Baltimore, Maryland, where it's hot and steamy. I've been working, as Sam said, with Sunrise for about 10 years, leading the Scandium alloy development effort. My background is in aluminum alloy design and development. Number of alloys that I've patented and taken all the way from the lab to full commercialization. So I'll talk a little bit about some of those opportunities today.
Thank you, Tim. Excellent. All right. As of you who are familiar with our company know, we have a relatively diverse portfolio of projects. Today's focus will be around our Scandium rather than the nickel cobalt and our exploration work. And as I said, the focus today is around markets. The way we'll structure today's presentation is to talk a little bit about the Scandium market. I'll then hand over to Tim to talk specifically about Scandium and alloys, which we see as undoubtedly the largest potential growth market for Scandium in a variety of applications. And once Tim has presented that, we'll move back just to talking briefly about the project and some updates on the project since the last presentation. We'd like to do this relatively quickly so we can give you some Q&A time at the end. And as Craig said, feel free to put your questions in through the Zoom call. All right, moving to the Scandium market. For those of you who are not familiar with Scandium, it is classified as one of the rare earth elements. It is a transition metal and very light. It has extraordinary abilities to change the properties of other elements and compounds on the periodic table. And in particular, the focus today will be on its ability as an alloy in aluminium products. But it also does have very important properties for microelectronics. Interestingly and importantly, Scandium has never been produced from a primary Scandium mine anywhere in the world. This remains a very small market globally. Only roughly 50 tonnes of Scandium oxide equivalent material is traded across the world. So that presents unique challenges, particularly for mining projects where scale is quite important. But since sort of first encountering this market almost 8 years ago, there is no doubt that it has grown. Its strategic importance in a range of industries has also grown, and the time, we believe, is now right to start considering mining as the preferred source of global Scandium supply for a range of industries, and this is what we are trying to do through Syerston. Next slide, please. Just quickly on sort of the demand side, as I said, about 50 tonnes of Scandium oxide equivalent is consumed annually. We've broken it down here by application. By far the largest use still is in fuel cells, solid oxide fuel cells, where Scandium is used to stabilise ceramic electrolytes. These fuel cells convert usually hydrocarbon, like a natural gas, into electricity, and they're very versatile for remote location power generation off the grid. So if you think of things like AI data centers, if you think of server farms, if you think of mine sites, anything in a remote location that needs reliable, sometimes off-grid power, fuel cells are a terrific application. And as you can see, it's still a large part of the scandium demand. The piece that is growing still small is in radio frequency filtering devices. Scandium is principally consumed here as a metal, a pure metal. And for those of you who remember on your mobile phones, that transition we had from 3G communications to what is now principally 5G communications on our handsets all over the world, what has made that possible is scandium. Its ability to enhance the piezoelectric properties of these radio frequency filtering semiconductors that go into our phones, into our mobile architecture and hardware has been extraordinary, and it will be the material that will enable the leap to 6G communications technology as well. And as far as we can tell, there is almost no substitute for this material at these radio frequencies that we're now operating in, so it's incredibly important in the chip industry. The third segment, which we'll spend most of our time on today, is the aluminum alloys. We see this as by far and away the largest growth opportunity for scandium, and we'll touch on why that is in the next few slides. On the supply side, these graphs look very similar for whatever rare earth element or industrial mineral you want to look at today. China dominates most of this market. Approximately 80% of primary chemical grade supply comes out of China. And when you're looking at refined metal for semiconductors, it's 100%. So there is a strong need, particularly in today's geopolitical environment, to find alternative sources of supply. And scandium is from Australia is a prime candidate for that. Next slide. Just to give you a sense, as I said earlier, scandium is not generally produced from mining. In China, it's usually produced from a waste byproduct of another industrial process. To date, most of that has been from the production of titanium pigment. So those waste products, as you can see, this is a hard cake that's been dewatered, but gives you a sense of the materials that are used. That typically gets re-leached and put back into solution to extract really small amounts of scandium in the waste stream, 10 to 20 parts per million. And how they manage that waste stream once the scandium has been recovered is also a rather big environmental challenge. But this is the way that scandium has been produced, and it's been manageable given the size of the market, tens of tons rather than hundreds or thousands of tons of demand. But as we see demand grow and the growing strategic importance of the metal, there are going to have to be other ways to put scandium into this supply chain. Next slide. And this is probably the most important point to take away probably before we get into Tim's section. The trade landscape has completely changed the dynamic for a range of metals, but in particular scandium. As we've seen in the United States, we've seen a range of new tariffs imposed across a range of products, almost every product, but in particular critical minerals have been targeted, and that scandium has not been an exception to that. The landed cost of scandium now into the United States with tariffs is exceptionally high. In combination with that, you're seeing, particularly in the defence sector, a real focus on foreign entity of concern tests. Any company or organisation wishing to supply the US government with materials now must demonstrate there is no foreign entity of concern that sits within their supply chain. Those tests are complex, difficult, and will be challenging to interpret as time goes on, but the policy intent is very clear. In the chip industry, you've seen extensive trade controls on the transfer of high-tech equipment, particularly chips manufacturing technology, and IP, and a very strong focus as part of the tariff initiatives to close transshipment loopholes. And you see the impacts of that in Southeast Asia and the tariffs that are being imposed there as well. In response to these, I guess, US initiatives, China's response has been swift, and insofar as it relates to scandium, very hard. In April this year, the Ministry of Finance and Commerce declared scandium a dual-use item with a range of, I think, 6 or 7 other rare earth elements. They've identified those elements as being particularly important in the US supply chains, and therefore they were prioritised for treatment as dual-use items. Dual use in the sense that most of these materials have both civilian and military applications, and therefore, in MOFCOM's eyes, deserve a heightened level of scrutiny in terms of trade arrangements. It's meant that there's been no scandium exports out of China since April. The market in the US for scandium materials now is extremely tight and difficult. A new reporting regime has been put in place under Chinese trade regulations, which will be enforced extraterritorially. And those notification requirements are, when you read the regulations, extremely prescriptive and draconian. So it will be interesting to see, even once scandium export quotas are lifted and provided to exporters, how US customers will respond to these new regulations. And as you can see from the last bullet point on the right there, the intention is to ensure that wherever Chinese scandium ends up in the supply chain and in final products, these new export regulations will have extraterritorial effect, even if they only incorporate, intermingle, or use Chinese scandium. So the trade landscape has changed considerably, and there are concerted efforts in Western supply chains to find new alternative sources of supply. At that point, it's a good opportunity, I think, or time to hand over to Tim to talk specifically about the alloy market. Tim, over to you.
Sure. Thanks, Sam. Oh, can you go back? Well, that's fine. So the R&D effort at Sunrise that I've been leading is focused primarily on optimizing scandium additions in commercial alloys. Scandium really can be added to almost every alloy out there. So it's not as if it is a scandium alloy, it's a scandium containing aluminum alloy that we're looking to develop. And principally what we're looking to do is improve performance and reduce manufacturing costs hand in hand. To do this, we're working with university industrial partners, primarily to resolve some issues that we feel have limited wide-scale adoption of scandium. If we get into specifics, scandium is the most potent alloying addition that you can add to aluminum. It does a lot of wonderful things, increases strength while improving manufacturability, also improving weldability, and which now leads us to better 3D printing. We're looking to use the increased strength and increased manufacturability to find applications all the way from automotive to aerospace, and also 3D printing. Scandium improves performance in aluminum alloys by interacting with the microstructure in a number of different ways. We kind of refer to this as the 4 pillars of scandium. On the lower left is improvements in solidification. What that does is it allows better weldability and better 3D printing. This property was utilized very early on by the Soviet military. They were able to add scandium to some high-strength aerospace alloys and weld cockpit and fuel tanks in the MiG-29. So that was kind of a very early application. That has not really transferred over to the West, but it is proof that scandium does dramatically improve solidification. What that does lead to now is improvements in 3D printing. So with scandium additions, you're able to print much, much higher strength aluminum alloys, both net shape and near net shape printing. The next one over is increased recrystallization. It basically stabilizing the grain structure in the material. What that allows you to do is heavily work an aluminum alloy, draw it down into very thin sheet or very thin tubing. This property was utilized back in the 90s in some sporting goods, kind of a niche application, but in sporting goods, some very, very high performance alloys. We're now seeing applications for this in some battery casings and some battery component applications. The next one over is dispersoid strengthening. As I said, it's the most potent alloying element you can add. You form very potent strengtheners. This property has allowed 3D printers to print alloys that have strengths comparable with aerospace 7075 type alloys. The next one over is nucleation of strengthening phases. Aluminum alloys are primarily strengthened by an aging step that's done after the heat treat or after the material is formed. What this allows you to do is get much, much higher strength in as formed properties or as formed alloys, and also it maintains strength at elevated temperatures. Next slide, please. So scandium, as Sam was saying, scandium is typically recovered as an oxide. It's not a cheap metal. The fact that it's an oxide, so scandium oxide is currently what comes from all recovered and refined sources. That is fine for the solid oxide fuel cell market that Sam talked about, which right now is about 70 to 80% of the market. If we want to use it in alloys, the oxides need to be converted into a metal or an aluminum scandium master alloy. This is an expensive and inefficient process. You lose a lot of scandium along the way. It's somewhat expensive to begin with, so you don't want to lose it. One of these routes actually uses HF for the conversion. So that's one of the areas that we're looking at, is different ways to make the scandium for master alloys. Next slide, please. So I mentioned some of the early work in the Soviet Union. They were using very high strength aluminum lithium alloys, and this is specific to the aerospace market. Lithium containing alloys are expensive on two levels. One is the lithium, it increases the cost. The other is you need to do very specific separate cast houses to make aluminum lithium alloys. The scandium addition can be used in any alloy, in any cast house. So we're not looking at a higher cost of manufacture. We're just looking at the cost associated with the scandium addition. And what we're looking at on the graph here is the effect of scandium level on cost in the billet. What we're showing here is the black line. These are different prices for scandium oxide. Historically, scandium oxide has been around $1,500 a kilo. At some points, it's been up as high as $5,000 a kilo. So what we're trying to do in our development efforts is lower the scandium level as low as we can to still maintain performance and optimize the cost. Historically, alloys had about 0.25 weight percent scandium. We're pushing that down as close to 0.1. So the important takeaway is if we have about 0.1 weight percent scandium with an oxide price of about $1,000, we add about $1.50 a pound to the billet cost. The current LME price is about $1.30, $1.20 a pound. So essentially we're doubling the price of the alloy billet. The main issue here though is in high performance extrusions, there's a lot of cost associated with the extrusion process. So increasing the price of the billet doesn't necessarily dramatically increase the price of the final product. We're working very hard with end-use customers to make sure that we're optimizing the buy-in of the scandium. So getting the best bang for the buck and allowing the scandium to buy its way into the application. Next slide, please. So as Sam said, we've been working for quite a while, a long history of partnering with a number of, typically a combination of a commercial company and university. Initial work back before COVID was a joint program we had with Chongqing University and Chinalco, looking to develop aluminum scandium alloys for automotive, but primarily aerospace applications. That work was very successful. Unfortunately, we don't know exactly where some of that has gone, but we were very successful in the work. Had a long program with Deakin University and UAC Corporation, focused initially on developing extruded parts for commercial aircraft. A very nice patent came out of that work for warm temperature alloys, so for use in nacelles and engine components. Been working with KBM AFLIPS for the whole time I've been working with Sunrise, and then before. KBM is a major supplier of master alloys. So they are kind of the one that is currently supplying to the West. There is another company in the US that's coming online that is also supplying. Worked with Airbus on a number of levels. Initially looking for a aluminum mag scandium alloy to be substituted on fuselage structure. That work is still ongoing, working with them on supply, potential supply. Recently, we've been working on helping them develop a supply chain for what's called the Scalmalloy alloy, an alloy developed at Airbus for 3D printing. That alloy has seen and is currently seeing a lot of adoption in the U.S. aerospace market, U.S. aerospace and military market. You see Deakin come up a number of times here, working with Deakin on developing, and this next one here was developing a family of aluminum silicon scandium alloys for electric buses. Also working with Deakin, Michigan Tech, and Monash more broadly to develop alloys for automotive applications, high performance scandium alloys for automotive applications. Currently working with UACJ in Japan, looking again at heat resistant scandium containing alloys for primarily automotive components. We worked with Relativity Space, developing a supply chain and also looking at some scandium containing wire alloys for printing rocket structures. And finally, the one that's a little bit different than the alloy design side, we're working with Metallysis and Kurt J. Lesker to develop the supply chain and some of the alloys for deposition of the thin film aluminum scandium nitride thin film materials for iPhones. Next slide. So out of all this work, our portfolio, our patent portfolio is growing. The first one I think is very important for our commercialization efforts. We've developed a heat treatment for what's called the 6000 series aluminum alloys. These alloys are primarily used in automotive. Automotive is one of the largest markets for aluminum. And one of the things that has restricted that is scandium and silicon don't play well together. We've come up with ways to make that work, and we feel that this is going to be a very large application down the road in automotive. As I said, the last one I had on the last slide was a fabrication of targets, sputtering scandium containing aluminum sputter targets. We also developed an aluminum magnesium lithium scandium alloy. This is kind of a take on some of the early Soviet alloys that were used in the MiG-29, although we've modified it slightly for additive manufacturing, wire-based additive manufacturing in this point. As I said, in the increased stability of the microstructure allows us to make thin film for conductor foils with high conductivity and high thermal stability. And the last one is an aluminum mag scandium alloy developed for 3D printing with wire. Next slide. I think it's back to you, Sam.
Yeah, thank you, Tim. Look, that was a very good summary. I think if there's a key point I'd like you to take out of what Tim has just explained is that the alloy market for scandium is certainly growing. We work a lot with customers and partners in this space. And what we are seeing in terms of adoption, particularly in 3D printed scandium-containing alloys is something that just didn't exist a few years ago. And the scale on which companies are looking to do this now, whether it's in aerospace components or other specialty applications, is large. The focus on automotive in particular is important. As I said at the start of this presentation, the scandium market is one of the world's smallest metal markets, and even a small penetration into a limited number of automotive parts will completely transform this industry. The volume requirements are enormous, but it is all about the cost point. As Tim said, the focus for us has been working on trying to find formulations and products that hit a particular cost point where scandium buys its way into almost everything. And this is why primary mining becomes important. The only way we believe you're going to achieve those cost targets for the industry are ultimately to be able to scale. And scaling is something the mining industry is very familiar with and very good at. So just turning quickly to the project in the last few slides. I won't spend a lot of time on this. Those of you who are familiar with our business will know it relatively well, but it is one of the most advanced, if not the most advanced, development-ready scandium project in the world. The mining leases are granted, excellent infrastructure supporting the project. All of the key utilities that are needed are available, and connection is underway. We own the freehold land rights surrounding the project, so we can have this project into construction and first production relatively quickly. We anticipate something of this scale, and it is a very small mine. It would be about a 2-year build. We could probably accelerate that to 18 months, looking at some early stage pre-development work as well. So this is something that is ready for funding and construction in the near term. Next slide. We've published previously the project's scandium-specific mineral resource estimate. The key point to note here is we've presented 2 different breakdowns at cutoff, 600 ppm cutoff, which focuses on approximately the first 20 years of production at a very high average head grade into the mills of about 660 ppm. Recall back to the Chinese waste supply, we were talking about 10 to 20 parts per million that need to be processed. So if you can find a high-grade natural scandium resource in the ground and you can mine it at decent scale, the opportunities for cost reduction are very large. But we've also applied a 300 ppm cutoff to what we refer to as our global resource. Here we have about 300 or 400 years of resource available at today's global consumption rates. A ridiculously large resource, but we expect this market as mine supply and expansion and reduction of cost in mine supply moves forward. We expect demand to grow from a global market of tens of tons to hundreds of tons and eventually thousands of tons of demand for scandium. So that resource, we believe, will underpin what will be a much larger mining operation in the future that will be able, with scale, to drive costs substantially lower and make scandium an extremely compelling proposition for most end users. We've announced recently also that the second phase of results from our recent drilling campaign will be due shortly, so we'll hopefully be able to update the market on those drill results next week or so. Thanks, Craig. So just in terms of the deliverables, we've done what we said we would do, which is to get this project ready for delivery and construction. The focus upcoming for us is completion of this drilling program to enable us to finalise the mineral resource reserve estimates and the mine plan. The feasibility study will be completed, we believe, or we estimate, by the end of Q3 this year. Offtake discussions are ongoing with a strong focus on US customers and obviously looking at US government critical minerals programs Many of you who follow this space will have seen that the US government in particular has leaned in pretty heavily in the last couple of weeks with the announcement on rare earths and MP materials and Mountain Pass rare earths mine there. There is US government funding flowing to the critical mineral space. For us, this is a relatively low cost, low risk application of US capital to solve what is one of their most important strategic issues and one of the largest supply vulnerabilities they currently have. So we will continue to work on that. And as Tim has indicated, we'll continue to work on our alloy development work with our customers and partners. Next slide. So for those of you who are interested in investment, and those of you who are shareholders, here is what you own. You own a high quality asset. There is no better scandium asset on the planet. It's advanced. It's in a location of low sovereign risk. And scandium now is an extremely strategic mineral. I'd like you to take away a few messages from today. The first is that this isn't a road to Damascus moment for us. We have been at this patiently for over a decade. In some ways, as a management team, it can be a little bit frustrating. But looking back, we've seen the way this market has evolved into being principally a market for one application only, which is fuel cells, with a little bit of metal interest, to one where metal interest is growing now very rapidly. A completely new market in semiconductors has emerged, and the strategic importance of scandium supply has really been emphasized now in the trade relationship that's unfolding between the US and China. So this project is very well placed to address a lot of those problems. The second message I'd like you to take away is that while this will be a very small mine by mining standards, there is an enormous volume opportunity here and a first mover advantage into the market to build a source of mineable scandium supply for customers. And thirdly, and most importantly, how I think about this as someone out of the mining industry, we have the ability with this resource to completely transform the cost structure of this industry. And that has been, with, I guess, the concentration of supply in one country, the key obstacle to seeing scandium grow. And this is what Syerston is intended to address: a large resource that is almost infinitely scalable to be able to produce low-cost material for customers. So I'll end it there. Thank you very much for those of you who've joined us, and we welcome any questions, and we can try to answer those if there are any.
Thanks, Sam. Thanks, Tim. Just a reminder for everybody, please use the Q&A facility at the bottom of the screen to lodge a question, and I will ask that to Sam and Tim. First one, Sam, to what extent will clean tech be involved in the Syerston project and the preparation?
Thanks, Craig. A good question. For those of you who aren't aware, Sunrise Energy Metals used to be Clean Tech Holdings Limited. And in 2022, we demerged a separate division of that company into what is now Clean Tech Water, a separately listed ASX company. And we adopted the name Sunrise Energy Metals. So there is a very close relationship between the two companies. The metallurgical testing and piloting that was undertaken for this Scandium project was undertaken by the former entity, the former Clean Tech Holdings Limited. So a lot of the knowledge and technology and engineering capability for building what will be a scandium recovery circuit still sits partially within Clean Tech. They will continue to work with us on the engineering component of this project, and it will continue to be focused around an ion exchange system. Interestingly, when we first looked at this project, everyone scratched their heads when they heard ion exchange. No one knew what it meant. The world has changed a lot in 6 or 7 years, with ion exchange being the primary piece of technology and kit that extracts lithium from lithium brine operations all over the world today. Cleantech has built a number of ion exchange plants for global clients, both in metals recovery and water treatment. It's a proven, well-tried, highly efficient technology, and it works really well for Scandium. So yeah, we will continue that partnership with Cleantech around the engineering part of this project.
Thank you. Next question is, scandium and antimony are possibly to be used in quick charging solid state batteries. Could you please outline the prospects for this application?
I actually was not aware of those metals in solid state. We have looked at scandium alloys for electric vehicle battery casings to protect the battery, but not so much as a component of the batteries or the cells themselves. Tim, are you aware of any of that?
I am not, and as you said, protecting the cells, and also, the one of the advantages, you can dramatically increase the strength of the alloy and still keep conductivity. So I think as all the leads and electrodes and all those things, yes, but as far as actual scandium and antimony, I'm not aware of that.
Sorry about that.
No worries. Next question is just around the Department of Defense in the US. They've been engaged in a few of the rare elements that are out there. Has there been any interest from the Department of Defense in Scandium, and in particular the Syerston Scandium project?
Well, we've engaged, I guess, with multiple programs in the US who have a focus around this. Some of them are Department of Defense programs. I mean, Tim, being based in the US, you see a lot of this. You've worked with agencies in earlier iterations of your career around stockpiling, logistics, Defense Logistics Agency. Maybe do you want to give a bit of just a short summary of how you see the Department of Defense working in this space?
Yeah, I think the one main thing that you mentioned a couple of times, Sam, is the fact that this market is evolving. Initially it was just the solid oxide fuel cells and a few alloy applications. The chip application and some of the 3D printing applications have really increased the need for scandium by DoD. And I think, previously they've been aware of scandium, but they haven't really used it. They haven't really felt that there was a need for it in their systems. So as a result, they weren't too concerned about getting it and having a supply. I think that's changed dramatically, both on the 3D printing side and the chip side. So they are now keenly aware of the fact that all of the scandium, at least all the scandium metal, is coming from China only. And I think it's really ramped up. From what I'm hearing in DoD, there's a really strong emphasis on getting a hold of scandium.
Yeah, and we have seen the publication of white papers, so we're not betraying any confidence there. DoD often publishes white papers for further research into particular areas, and scandium has certainly been one of them recently. In the chip industry, I guess in the chip sector, we've seen DARPA, the Department of Defense's sort of key research institute, run a very large program around modern battlefield communications technologies, where scandium is going to be at the heart of a lot of that, what they call wide array radio frequencing filtering technologies, which are focused on battlefield applications. So, there is a lot publicly being announced now. But as I always say, the fact that China decided, out of all the elements it could decide to put restrictions around back in April, picked scandium as one of the handful. They understand the importance of this metal better than anyone. And, the moves may be late by the US, but at least they're happening now, and things will start to move.
Thank you. Next question in from an attendee was they read an article which discussed the potential for the use of scandium isotopes in radiopharmaceuticals. Any comment on this from a potential end use, please?
Oh, you're really pushing my limits now. Tim, do you want to start with that one?
Yeah, I think that's definitely out there. I have seen some references to that, but I think one of the important things that I pointed out is right now 70 to 80% of the market is scandium oxide. So getting scandium metal, which would be the first step in this radioisotope application, you need to convert the oxide into metal. And right now, the only people doing that are China. So, I think there is potentially an application once we get scandium metal production up and running.
I tend to stay away from companies or markets where I have to inject things into people. The only other health and safety issue we had was Tim was the developer of the early scandium alloys for baseball bats, and I think he endangered the lives of many young children.
Yes.
During school leave with those bats.
Yes.
A bit overpowered. No, I expect that will be a relatively small volume market, but very niche. But yes, it's coming.
Thanks. Now, there's been a few questions just around the process flow sheet for Syerston, so I'll lump 3 or 4 questions together into one. So forgive me with a bit of the disjointed nature of this question here, but or maybe it's easier. Can you talk through the process? Will HPAL be used? Will RIP be used? If you can just give a bit of an understanding of the flow sheet for the scandium, please.
Yeah, the flow sheet is very similar to the earlier feasibility study we published on Syerston. So effectively 3 separate circuits. Well, let's say 4. There's a front end crushing circuit, but remember, this is not hard competent rock. This is more like dirt we're digging. So we're just sort of crushing it to very fine, well, to a slurry. The slurry then is injected into an autoclave. This is an extremely small autoclave. It's nothing like the big nickel, cobalt, laterite autoclaves you see that process nickel and cobalt. It's actually a very small unit, but we are targeting relatively high extractions of scandium, somewhere around 90+% out of the autoclave. So the scandium then goes into solution under heat and temperature and acid. The slurry that then is ejected from the autoclave moves into an ion exchange circuit where it's contacted with ion exchange resins as a pulp, the slurry, so high solids content, and the resins or the little beads that operate in that moving bed ion exchange circuit selectively pull scandium out of solution. Now that's a very extremely efficient circuit that operates at about 98%, 99% recovery. I guess ion exchange has been used for decades. The difference here is we're using a moving bed system rather than a fixed bed system. It allows us to regenerate the resins on the move and a much higher extraction efficiency. And then once the ion exchange resins have extracted the scandium, we put them through a pH shift to drop the scandium out of solution, and we then put them through a refinery at the back end, effectively a purification circuit to remove any remaining impurities. And what you're left with at the end is a very high purity scandium oxide.
Thanks. Next group of questions is just around offtake and potential partners. So if you maybe just talk through what the plan is for offtake for the Syerston project, and have you entered any MOUs yet with end customers?
We've had, I'd say, numerous discussions with a range of customers across those different market sectors we talked about earlier. There is a very strong level of interest for offtake. We have, yes, received expressions of interest. Where most of the work still to be done is around the feasibility study. where most prospective customers, most are interested in supply. Most would like to see completion of the feasibility study to get an understanding of where the economics of the project lie. To be frank, while offtake was a really important part of the early discussions around financing for this project, what we've seen in the US more recently through government and government programs really does change the landscape for critical minerals, and particularly rare earth metals like this. There's a much stronger focus now on strategic stockpiling. The US government's already been very clear about its desire to build stockpiles for a lot of these materials. So it's not a conventional off-taking environment we're finding ourselves in the moment, but we're not concerned that offtake is going to be an issue for this project, given the amount of interest we're seeing from industry.
Thanks. Next one, probably for you, Tim. Do you see the use case for 3D printing based applications for the aluminium scandium alloys become the largest use case for scandium going forward?
I think in certain aerospace applications, I think that the 3D printing with scandium containing alloys will definitely take off. Right now in the aerospace, take a big block of metal and throw 90% of it on the ground is kind of the way to make a lot of parts. 3D printing offers a lot of advantages where you can do some interesting things with inside structure and have a part that's basically ready to go on the aircraft right away. In this case, scandium really offers two things that no other material can offer. One is it improves the printability. You don't get hot tearing and cracking, which is one of the big problems with aluminum alloys. The other one is when you print these very complex shapes, typically you have to take an aluminum scandium or aluminum alloy and take it to very high temperature and then throw it into water, which causes extensive distortion. The scandium containing alloys, we can reach the same strength as you would see in an aerospace alloy without the quench. So, I think in aerospace, that's a place where 3D printing will definitely take off. Our main focus in automotive is more in crash structures and trying to replace steel in the lightweighting efforts that are ongoing with EV vehicles. So I think in automotive, I would say probably not. In aerospace, I think it'll be the first one that gets a toehold, and then hopefully we grow into the structure itself.
Thanks, Tim. Sam, next one for you again, just pulling a few questions together into one here. Can you give a bit of an update, please, to the timeline for the feasibility study at Syerston? And if approved, how long do you think construction timeframe for the project would be?
So we've indicated the plan is to get the feasibility study out by the end of September this year. From final investment decision to first production, as I said, it's probably about 2 years. If we can finance some early phase pre-development work, then there's the capacity maybe to shrink that a bit to probably at best 18 months. But it's roughly a 2-year build.
Thank you. And just conscious of time, last question. This has been asked a few times by people, so I've been saving it for the end. Sam, any comments on the recent share price move? What do you think has been causing the upwards trajectory in Sunrise's share price recently?
Well, I think there's a much greater awareness of how important scandium is. The recent capital raise we did saw three really effectively US-based or US national shareholders decide to cornerstone that placement and that raise. So it's very hard in the market out here in Australia to get a very good sense of what is happening in the United States. But things are starting to move very quickly now. And there is, I think certainly from US investors, a real appetite to look at companies like Sunrise Energy Metals that have high quality development ready assets that can get into market quickly and service key strategic industries, they want to support those. So yeah, that's part, I'd say, of the big geopolitical picture of why this is important. I think as the other thing is we continue to drill this out and find more and more high grade scandium, which will underpin the cost base of this business. And as I say, it's going to be the ability to produce at low cost that will drive volume in this market, because we can price to a point where scandium then buys into very large scale applications. So to me, it's always about first mover advantage in these smaller markets. We're very focused on getting the feasibility study done, the project financed, and then getting into construction as quickly as possible.
Excellent. Thank you, Sam. Thank you, Tim. That's the end of the questions. Sam, just quickly back to you for any final comments.
No, to all shareholders who are on the line, thank you very much for your continued support of the business, and the management team is very focused on making sure we realise value for you.